Hello students. Last class we have discussed about unit cell and its types. We have discussed about simple cubic unit cell, body-centered unit cell, face-centered unit cell and end-centered unit cell. In today's class, let us study about how to calculate number of atoms per unit cell. It is because last class we have told that a complete crystal lattice will be comprised of about 8 unit cells. Hence, one atom present in the corner will be touching 7 other unit cells. Therefore, we have to now calculate how many atoms will be there if you take one unit cell out of a complete crystal lattice. So, first we shall discuss about calculation of number of unit cell in simple cubic. So, in a simple cube, you know that there are 8 atoms present in the corners. Each corner atom will be shared with 7 other cubes in a crystal lattice. Therefore, the contribution of the corner atom towards a particular unit cell will be only 1 by 8. So, the total number of atoms in one unit cell of a simple cube, 8 corners, and from each corner to the one unit cell will be 1 by 8. So, 8 into 1 by 8 is equal to 1 atom. So, how many atoms per unit cell is there in a simple cube? It is 1 atom. Even though there is 8 corners, the contribution from one corner towards one particular unit cell will be only 1 by 8. See this picture. This is one unit cell. Here you can see that this corner is in contact with 7 other unit cells to make a complete crystal lattice. Therefore, when you take out one particular unit cell of a simple cube, from each corner 1 by 8, 1 by 8, 1 by 8, 1 by 8, 1 by 8 and 1 by 8. When all these 1 by 8 1 by 8 when joined, that will be equal to 1 atom per unit cell. So, number of atoms per unit cell for a simple cube is 1. Now, let us move on to body-centered unit cell. So, what is BCC or body-centered unit cell? In BCC or body-centered unit cell, we are having 8 atoms as usual in the corners plus 1 atom in the center of the cube. The center atom is not being shared with any other cube. Therefore, to calculate the number of atoms per unit cell of BCC, we shall first do with the corner atoms. So, in corner atoms, we have got 8 corners into 1 by 8, that is equal to 1 atom plus central atom which is not shared with any 1 atom. So, total what is it? 1 plus 1 is equal to 2 atoms per unit cell. So, in BCC, we have got 2 atoms per unit cell. 8 corner atoms. From 8 corner atoms, only 1 by 8 each atom will contribute towards one particular unit cell. 8 into 1 by 8 plus body centered. See, body center atom is 1 atom. So, total 1 plus 1 is equal to 2 atoms per unit cell. See the picture. So, these are the corner atoms which we have got here. When they all join, that is equal to 1 atom, and the central atom that is not shared with any other unit cell. Okay. So, this is ball and stick model which is easy for us to draw in 2 dimension to have a clear cut picture. 8 corner atoms we are having, in which only 1 by 8 is contributed to one particular unit cell. Then in the central atom. Now, face-centered unit cell or FCC. In a face-centered unit cell, you know that 8 corner atoms are present plus there are particles at the center of each face. Now, tell me students, how many faces are there for a cube? See, you are sitting in a room which is equal to a cube. Just count how many faces are there. 4 walls are there, 1 floor and 1 roof. So, total 6 faces are there in a cube. If a particle is present at the center of that face, that particle will be shared with how many cubes? Yes, 2 cubes. Okay, that is one wall is shared between 2 rooms. So obviously when a particle is present at the center of the face, that particle will be shared between two cubes. Hence, the contribution of a particular particle to a particular cube will be only half. So let's see. Now for a face-centered cube, we have got 8 corners into 1 by 8 from each corner, that is equal to 1 atom. Then we have 6 face into half per face, that is 3 atoms. So what is the total? 1 plus 3 is equal to 4 atoms. See? So for a face-centered unit cell, the number of atoms per unit cell will be 8 corners into 1 by 8, that is equal to 1 atom, from 6 faces into half contribution from each faces, that is equal to 3. Then total number will be equal to 3 plus 1 is equal to 4 atoms. So in FCC we have 4 atoms per unit cell. See, this is the picture. So in the picture it is clearly seen. This is the contribution of the atoms from the face. So only half is inside the cube. This half will be in the other cube. Okay. Now these are the corner atoms, 1 by 8 at the corners. In this picture. This is clearly visible. Now this is ball and stick model of FCC, which it will be easy for us to draw in the new 2-dimensional way. So these are the corners, 1 by 8 is contributed, and these are the particles at the center of the faces, in which half belongs to one cube, other half belongs to the neighboring cube. Is it clear? Now let us discuss some numericals based on these number of particles per unit cell. So here is a question. Yeah. A cubic unit cell is made of 3 elements, X, Y, Z. Atoms of X are present at the corners, atoms of Y at the center of the cube, and atoms of Z at the center of each faces. What is the formula of the compound? So we are having a cube which is made of 3 elements, X, Y, Z. In the question it is clearly mentioned, X atoms are present at the corners, Y atoms at the center of the cube, and Z atoms at the center of each faces. Now let's calculate the formula based on the unit cell concept. So here, from the corner, what will be the contribution of our X atom? 8 into 1 by 8, that is equal to 1. Then for a unit cell formula, for Y atom, at the center, Y atom is completely present inside the cube. It is not shared with any other cube, so the contribution is 1. Then for Z atom, it is present in the face, therefore the number of Z atom per unit cell will be 6 into 1 by 2, that is 3. Therefore, what can be the formula? Can you guess, students? Yes, it is XYZ3. I hope it is clear. So for X atom, since it is in the corner, the contributions to per unit cell will be 8 into 1 by 8. So 1 atom we can calculate. Then at the center it is Y particle, and at the face we have Z, which is shared between 2 cubes. Hence 6 into 1 by 2, 3. So what is the formula? XZY3. Now let's move on to next problem. Yes. A unit cell consists of 2 elements, P and Q. Atoms of P are present at the corners and face center. So atoms of P are present at the corners as well as face center, while Q atoms are present at both on edge, not end, it is edge, center and body center. What is the formula of the compound? So here we are having a compound with 2 elements, P and Q. P is present at the corners as well as at the face, whereas Q is present at the edge and body center. Now tell me, students, how many edges are there for a cube? So what is an edge? Where 2 faces will meet, that point we call it an edge. Okay, so how many edges are there? Yes, we have got 12 edges in a cube, and one edge will be contacting with 4 other cubes. So one edge is in touch with 4 cubes. So 1 by 4 only will come towards one cube. Let us see how to calculate now. See, for P atom, 8 into 1 by 8 because it is present in the corner, plus it is present in the face also. So 6 into 1 by 2, face contribution. So 1 plus 3 is equal to 4. Next, for Q. For Q atom, we have 12 edges. And for the 12 edges, contribution is 1 by 4 towards 1 cube. Plus 1 at the body center is present. So 3 plus 1 is equal to 4 for Q atom. Now what will be the formula? Yeah, P4 Q4. So when the both are 4, it gets cancelled. Therefore, formula of the compound is PQ. So listen once again. We have got two atoms, P atom. P atoms are present in the corner plus at the center of the face. Therefore, 8 into 1 by 8 corner plus 6 into 1 by 2. 1 plus 3 is equal to 4. Q atoms are present in the edges. 12 edges are there and 1 by 4 towards 1 cube. So 12 edges into 1 by 4 plus 1 at the body center. So 3 plus 1 is equal to 4. Hence the formula will be PQ. Hope it is clear for you all. Yes. Now we shall move on to the third problem. Two elements A and B crystallizes in the cubic unit cell with atoms A at the corners and atoms of B at the face center. So the first statement states that we are having two elements A and B. A atoms are present in the corners and B atoms are present at the center of the face. Now see the twist. If two atoms of A are missing, so from the corners 2 atoms of A are missing from the corners and 2 atoms of B are missing from the face center. So A atoms are also missing, B atoms are also missing. Now you have to tell the formula of the compound. I shall explain the question once again. We are having a cube with two elements A and B. A atoms are present in the corners, okay, but 2 atoms from the corners are missing. B atoms are present at the center of the faces, but here also 2 atoms are missing for B. Now let's see what can be the formula of the compound. See. Now for A atom, we are not taking 8 into 1 by 8. We are taking 6. Why 6? Because we don't have 8 corners now. 8 corners are there, but particles are not present in all the 8 corners. 2 corners are vacant. So we are taking 6 into 1 by 8. Is it clear? Not 8 into 1 by 8, it is 6 because only 6 corners we have got atoms. 6 into 1 by 8 is equal to 3 by 2. Now for B atom, 6 faces are there, but all the 6 faces B atoms are not present. So we are taking only 4, 2 minus. 4 into 1 by 2 is equal to 2. Now what is the formula? Say A is to B, 3 by 4 is to 2, that is equal to 3 is to 8. Hence the formula of the compound is A3B8. That is the formula of the compound. So listen once again, for A atom we are not taking 8 corners because it is told in the question that 2 atoms or 2 corners are kept vacant. So 6 into 1 by 8 is equal to 3 by 2. For B atom it is 4 into 1 by 2 because again 2 faces are not having any atom. 4 into 1 by 2 because is equal to 2. Therefore A is to B is equal to 3 by 4 is to 2. If you rearrange, you get 3 is to 8. A3B8 is the formula of the compound. Okay. Now from here we are going to another concept of how to arrange the particles in a solids. So arrangement of particles, let us discuss. First we will start with one dimension arrangement. So we have to, from one dimension we should move on to 2 dimension, from 2 dimension to 3 dimensional arrangement. So arrangement in 1 dimension means in 1 axis, right? You can take as x axis. So particle arrangement in 1 dimension. Okay, closed packing of spheres in one dimension will appear like this. Suppose this is x-axis. So, in one dimension particles are arranged. Now, in two dimension. Two dimension means in the y-axis also particles to be arranged, right? Yes. So, close packing in two dimension. So, here the point is that when you are placing the second layer, so one dimension to two dimension, second layer can be placed in two ways. Which are the two ways? One way in which just below the first layer we are placing the second layer. This is the first layer, and just below the first layer if you place a second layer, we are going to get AAA type. Another way we can place a second layer is that in between these two first layer we are placing the second layer. That means in between the gaps of the first layer, second layer is placed. So, that layer will be different from A layer. Again, third layer will be the repetition of first layer. That is known as AB type. See the picture here. This is AA type. See, first layer is there, second layer is perfectly placed below the first layer, third layer is also same. Hence, we are going to get a square close packing in two dimension. Square close packing in two dimension. Now, see this figure. First layer we have, second layer is placed in between the gaps of the first layer. Third layer also in between the gaps of the first layer, second layer which is resembling the first layer. So, AB type, which we call it by the name hexagonal close packing in two dimension. So, two dimensions we have two type of close packing. One is square close packing AA type, and then hexagonal close packing in two dimension AB type. See, square close packing AA type. See why it is called square close packing. See, if you focus one particular particle and you can see that that is in contact with four other particles which is looking like a square. So, this type of arrangement in two dimension we call it by the name square close packing. Now, you see here hexagonal close packing in two dimension. So, if you focus one particle, this particle is in contact with 6 other spheres which looks like a hexagon, AB type. I hope you understood what is AB type. See, first layer and second layer will be kept in between the first layers. Like that we get hexagonal close packing in two dimension. Is it clear? So, we have studied one dimension and two dimension. In two dimension, two type of arrangement is there. Square close packing in two dimension AA type, and hexagonal close packing in two dimension AB type. Now, what is next? Yes, three dimensional packing. But before going to three dimensional arrangement, I would like to talk about another topic here, coordination number. Okay. So, coordination number for all the close packing is very important. What is coordination number? The number of the nearest neighboring particle of a particular particle. That means one particular particle is having how many other particles in contact with it. That is the nearest neighboring particle. Neighboring particle, how many particles are it is coming in contact. That is known by the term coordination number. For one dimension, what is the coordination number? One particle is in contact with two other particles. So, 2 is the coordination number for one dimension. For two dimension, we have got two arrangement. One is square close packing, as we can see in this figure here. So, what is the coordination number for square close packing in two dimension? 1, 2, 3, 4. Yes, 4 is the coordination number for a particle in a two-dimensionally arranged square close packing. Then hexagonal close packing, as we have seen that 6 particles are being arranged. One particle is in contact with 6 other particles. So, coordination number for hexagonal close packing in two dimension is 6. I shall repeat once again. Coordination number means number of nearest neighboring particles. For one dimension, The neighboring particle is 2, that is coordination number is 2. For 2 dimension, we have got 2 arrangement, square close packing and hexagonal close packing. In square close packing, the coordination number is 4, and in hexagonal close packing, the coordination number is 6. Okay. Now, we can move on to 3-dimensional arrangement. Yeah. Close packing in 3 dimension. So, first we shall discuss square close packing in 2 dimension to 3 dimension. That means, we are now filling the particles in Z axis also, so that we get a complete 3-dimensional solids. First in single layer, then we put in double layer. Now we are going to raise it in the third layer up to get a 3-dimensional view. So, the square close packing in 2 dimension, when we convert that into 3 dimension, it will be looking like this. A primitive square close packing type, a simple cubic type, primitive square close packing, AA type. So, all they are in same line, A. Close packing 3 dimension obtained by placing 2-dimensional layers one above the other. So, you have got 1 2-dimension, next 2 dimension, again and again you get a 3-dimensional arrangement. Okay. So, in square close packing, we get a primitive square close packing arrangement. Now, in hexagonal close packing of 2 dimension, when we convert that into 3 dimension, hexagonal close packing of 2 dimension, converting into 3 dimension, again we will get 2 types. One is AB type, HCP in 3 dimension, hexagonal close packing in 3 dimension, AB type. I shall explain first. So, we are having particles in first layer, and then second layer is placed in between the first layer. We are having hexagonal close packing in 2-dimensional arrangement. Now, above that we are placing next layer. Next 2-dimensional HCP layer is placed. Now, where will you place? The second layer of HCP in 2 dimension is placed in between the grooves of the first layer. So, first layer A has 2-dimensional HCP layer. Okay. And the second layer A, B is placed on the depression of the first layer. Third layer is placed same as the first layer A. Is it clear? So, you see here, this is the hexagonal close packing of first layer. Now, second layer of HCP, we are placing in between the grooves. So, this is the gap. So, here I am going to place it. See, on the grooves are being covered. So, this is the second layer placed on the first layer. Is it clear? Now, this point, this is being covered. On the depression of the first layer is being covered over here. Is it clear? So, this is how we are going to place A, B. This is the B layer. Now, again the third layer will place above the B layer, similar to that of the first layer, that is AB type. Is it clear? So, we are having first layer of HCP, second layer will be placed in the depression of the first layers, and third layer again we are placing similar to the first layer, AB type. We are going to get hexagonal close packing in 3 dimension. Is it clear? So, and coordination number here is 12. This type of AB type of arrangement is seen in case of magnesium, zinc, cadmium, etc. See the picture here. Now, we are having A layer. This A layer, the B layer is placed in the gap. So, these are the gaps. See, B layer is placed. Again, the A layer similar will be placed. So, you will be getting hexagonal close packing in 3 dimension AB type. Now, coordination number. So, how many atoms a particular particle is coming in contact when arranged in 3 dimension. So if you calculate that, one particular atom, so this will be coming in contact with 6 atoms, so 3 atoms below, 3 total, you are going to get 12. 12 is the coordination number of hexagonal close packing in 3 dimension, HCP in 3 dimension. Now we are moving on to ABC type. So here what happened, we are having hexagonal close packing of 2 dimension as a base layer, A layer. Now second layer is placed on the depression of the first layer. A and B is ready. Okay, so first layer is hexagonal close packing of 2 dimension. Then above that we are placing B layer on the depression of the first layer. Now the third layer, C layer, is again placed on the depression of the second layer. Fourth layer similar to first layer. So A, B, C pattern will be getting. So first layer A in HCP arrangement, second layer is B placed on the depression of the A layer, and the third layer is placed on the depression of the second layer. Fourth layer similar to first layer. Okay, we are going to get cubic close packing arrangement or CCP. So 3-dimensional arrangement, we have got 2 types, HCP and CCP. For both, the coordination number is 12. In CCP, it is ABC type of arrangement, cubic close packing. Hexagonal close packing is HCP. We have got AB type. So coordination number of CCP is again 12. This type of arrangement is seen in atoms like silver, gold, copper, metals. So metals, almost all metals will be having CCP arrangement. See, we are having A layer over here. Now the B is placed in the depression of the A layer. C layer is placed in the depression of the B layer. So ABC type of arrangement is C. I hope it is clear to you. A layer, B layer, C layer. Then again ABC. That is the pattern followed to get CCP arrangement, cubic close packing arrangement in 3 dimension. Coordination number again is 12 over here. See, clearly it is visible. Layer A, layer B, again layer A. Hexagonal close packing in 3 dimension. AB, AB, AB will come like this. Coordination number is 12. Okay. So 6 here, 3 plus 3 in contact for a particular atom. If you focus on this red atom, 6 atoms, it is coming in contact of its own layer. It will touch 3 other atoms above the layer, 3 other atoms below the layer. So total 6 plus 3 plus 3, total 12 coordination number. In ABC type, A layer is there, B layer, C layer is a reverse, which is in the depression of the B layer. So A, B, C. Here also coordination number is 12. So if you focus on this red atom, 6 around here, 3 above layer and 3 below layer. We are going to get 3 plus 6 plus 3 again 12. Close packing in 3 dimension. So from 1 dimension to 2 dimension, 2 dimension to 3 dimensional close packing in solids we have discussed. In 2 dimensions, 2 type is there, square close packing and hexagonal close packing. When square close packing is converted to 3 dimension, we are getting primitive cubic structure. When hexagonal close packing in 2 dimension, when converted to 3 dimension, we get 2 type, AB, which is known as hexagonal close packing in 3 dimension, and CCP, cubic close packing in 3 dimension. Now, we have to discuss about voids. What are voids? Voids are the empty space between the atoms. Or you can say the opposite of lattice point also. What is lattice point? The point where you can find the atoms. So place in the crystal structure where it is empty gap, we call it as voids or interstitial space. Okay. So voids are the vacant spaces between the constituent particles in a closed structure. When you arrange the particles from 1 dimension to 2 dimension, 2 dimension to 3 dimension, we can see some small empty gap. That empty space, we call it by the term in solid chemistry voids. And Based on the type of voids formed because of this arrangement, let it be HCP or CCP, two types of voids are being seen. One is tetrahedral void or T void. Other one is octahedral void or O void. So two types of voids are there, T void and O void. Let's see T voids. T void or tetrahedral voids are formed by the help of 4 spheres. Okay. So this is the picture. We have got the base layer, then the top layer. So the top layer is placed above the depression. So if you turn that and see, it looks like a tetrahedral. So the other way, you should see the picture in the other way around. There will be a small gap. Okay. Here this is covered, but if you reverse the figure and see, there is a gap there. That is known as tetrahedral void. The sphere of the second layer is placed above the void of the first layer. Then when you reverse it, you can see there is a gap over there. That gap is known as tetrahedral void or T void. See how octahedral voids are formed. We are having 3-layer base and the 4th layer is placed depression with the 6 atoms. So voids of the second layer comes above the voids of the first layer. Okay, so we have got 3 atoms below and 3 above atoms are there. The such formed voids, we call it by the name octahedral void. And one more point is there, if there are n atoms in a crystal, the number of tetrahedrally looking voids will be 2n, double the number of tetrahedral voids will be there. Whereas in case of octahedral voids, if you see the calculation, when there are n atoms arranged, the number of octahedral voids formed as a result of this arrangement will be same as n number of particles. See in this picture, the tetrahedral voids and the octahedral voids are clearly visible. So tetrahedral void is formed with the help of 4 atoms, and octahedral void is formed by 6 atoms. So T voids and O voids. T void, O void. The number of tetrahedral void will be double the number of atoms present, and number of octahedral voids will be the same. Again, see the layers formed tetrahedral in shape. It is looking like this. The lower layer and the upper layer. Because of that, we are getting an octahedral void here, which is formed by 6. Don't take it as 8. 6 spheres are responsible for octahedral void formation. Looks like an octahedron over here. Then, if there are n particles, the number of octahedral voids will be n, and the number of tetrahedral voids will be 2n, double the number of particles. Then, let us see how this is being filled. How are the voids filled? Usually in a crystal. Formula of a compound and number of voids filled. If you are taking an ionic solids, in ionic solid, usually the negative ion or the anions will be big in size, and cations will be formed in the voids. So in ionic solids, bigger the ions, anions form the closed packed structure, and smaller ions, the cations, occupy the voids. If the cations are very small, it occupies tetrahedral void. If cations are big, it occupies the octahedral void. So tetrahedral and octahedral voids are occupied by cations in an ionic crystal. Now, let us have a problem based on these voids. A compound is formed by 2 elements X and Y. An element of Y is anion, which makes a CCP arrangement, cubic close packing arrangement. We are having anion atoms, CCP arrangement, and X is cations occupying the octahedral void. What is the formula of the compound? So we are having 2 elements X and Y. X atom is in the CCP arrangement, and Y atom, the cation, is in the voids. What can be the formula? See, it is already given. X is cation, Y is anion. Now, let number of atoms Y in CCP be n. We are considering that there are n atoms of Y in this arrangement, cubic close packing arrangement. Therefore, number of octahedral or O voids formed will be n voids, n holes or n empty spaces will be there. All the empty spaces are occupied by our X cation. So, since all the octahedral voids are occupied by atoms X, therefore what it will be there? Number of atoms of X is also n. X is to Y is n is to 1, therefore the formula is XY. Is it clear? See, once again I will explain. X is cation, Y is anion, and Y is CCP arrangement. So, Y anions are the major. If there are Y, suppose there are n number of Y atoms. When there are n number of Y atoms, how many empty voids will be there? There will be n number of O or octahedral voids. All the octahedral voids are occupied by X atoms. That is also n. Therefore, the formula is XY. Next problem. We are having an atom of element B, again HCP arrangement, hexagonal close packing, which will be anion. And those of element A, our cation is occupying only 2/3 of the tetrahedral void. So, all the tetrahedral is not occupied by A atom. Only 2/3 of the tetrahedral void is occupied by A atom. See the, let's start. Number of atoms of B in HCP, that is B atom in HCP B n. N atoms are there. Then how many tetrahedral voids are formed? 2n. In the 2n, therefore number of T void or tetrahedral void will be 2n. But all that it is not occupied by A atom. Only 2/3. See, since 2/3 T voids are occupied by A atom, 2/3 into 2n. That is 4/3n. 2/3 of 2n. 2/3 equal to 4/3n is it. Therefore, A is to B. A is 4n/3 is to n. Then what is the formula if you rearrange and we will get? The formula is 4:3 or A4B3. This is a formula. Once again I shall explain. Let number of B atoms in HCP Bn, it is anion, so that is major. Tetrahedral void formed, T void is 2n. But all the tetrahedral void is not occupied by A atom, only 2/3. So, 2/3 into 2n, 4/3n. Therefore, A is to B, 4n/3 is to n. Therefore, 4:3, A4B3 is a formula. So, with this we shall wind up today's session. Thank you.